Okay.
It's a recording.
Yeah, let's start. So today we will have the third lecture of Ashoke Sen. He will give a lecture on the D-instanton amplitude in string theory. Please.
Okay, thank you very much. So let me start sharing screen. Okay, is it visible?
Yes, yes, it's visible.
Okay, thank you. Okay, so yesterday we calculated the normalizing constant. Okay, so let me write down the. So we calculated this I to the a, but there is one assumption that we made. So this was calculated with one assumption. Okay. And that assumption was that for the open string tachyon, which we call psi 0, we integrate over half of the steepest descent contour. Over half. Okay. So the first thing I'll do today is to justify this. Okay, so we'll justify this. And to do that, you have to know something about the tachyon potential. So let me just tell you how it looks. Okay. So if you plot the tachyon potential, say V of psi naught versus psi naught, and you can think of this as an effective tachyon potential after you have integrated out the heavy modes. Okay. And for the D-instanton, this V is really the action because there is no momentum, right? So the action and potential, there is really no difference. Okay. And it has been known from early days of study of tachyons on unstable d-branes that the tachyon potential has a shape like this. So at the origin, psi 0 equal to 0, this is what describes the D-instanton solution. This is a D-instanton. Okay, of course, D-instanton should have psi 0 equal to 0 because that's where you start. Okay. But what you also know that there is a minimum, local minimum, okay, which describes the perturbative vacuum. Now, in all our calculation, of course, you want a full contribution from the perturbative vacuum, okay, because otherwise you will be inconsistent with perturbation theory. Okay. So this means, okay, this translates to the following statement that you have to include the full steepest descent contour of the perturbative vacuum. Okay, so this is also a saddle point of this potential, and you have to include the full steepest descent contour. Okay. And that full steepest descent contour turns out to be the following. Let me draw it maybe in thick line. So it's basically this part over here. Okay. So this part of the real axis must be part of the integration contour over psi 0. Now there is also another thing that you know about the tachyon potential is that as psi 0 goes to minus infinity, then V of psi 0 goes to minus infinity as psi 0 goes to minus infinity. In other words, the tachyon potential is unbounded on this side. So this means that e to the minus s of psi 0, okay, which is in this case e to the minus v of psi 0, that goes to infinity as psi 0 goes to minus infinity. So this tells us that we cannot get a consistent theory by taking the integration contour to be along the negative real axis, because the integrand will blow up as you go towards psi 0 equal to minus infinity. So that's not a well-defined integral. So with a little bit of thought, one can show that the consistent integration contour, okay, on the negative side is essentially the following. It basically goes like this, okay, and then it will, of course, deviate from the imaginary axis because of the higher order corrections, but it's roughly like this. So this is, and if you compare this with the steepest descent contour of the instanton, okay, that goes like this. Okay, that's symmetric, and that goes like this. Okay, it goes up and turns around. So what we say is that the integration, the full integration contour includes the full steepest descent contour of the perturbative vacuum, okay, which reproduces the perturbative amplitudes. In fact, the Borel-Lissam version of the perturbative amplitudes. And the instanton contour, and this part of the contour, okay, gives half the steepest descent contour of the instanton. Okay, so this is half of the steepest descent contour of the instanton. So this essentially is the justification as to why we include half of the steepest descent contour of the instanton, okay, because you want to include the full steepest descent contour for the perturbative vacuum, okay, in order to be consistent with perturbation theory. So this is as much as I'll say about this factor of half. So I'm now going to turn to the next set of problems, but are there questions at this stage?
So the right part of the contour does not contribute, or
yes,
or
so this is part of the perturbative contribution,
which is not divergent, or
which is not divergent. In fact, the BROI, what they showed is that because they have the matrix model result, right? So they check the perturbative results to first order, and then they showed that if you take the matrix model result and do a perturbation expansion, then that perturbation expansion is Borel summable, and it gives you some answer. So they subtracted the full answer from this Borel sum perturbative answer, and that's what they identified as a D-instanton contribution.
I see. So, and that does not include the right part of the contour.
Yeah, so that does not include the right part, because the right part is the Borel-sum version of the perturbative answer.
Okay. And I have a second question about this. So when you are deforming the contour on the left-hand side, this means in the complex psi 0 plane. And I guess you're also analytically continuing the potential to that region? Or?
Exactly. Yeah.
Okay.
Because I mean, if you include, that you have to do in any case when you do the steepest descent contour, right? Even if you look at lowest order, you are going along the imaginary axis. So you are already analytically continuing the potential in that case, right? Because you have this e to the half psi 0 squared, and you integrate it along the psi 0 equal to imaginary axis. That's like analytic continuation to the imaginary axis.
Right. The potential is obtained from string field theory, though. Right?
Yes, indeed. So this is the first term. This is the first term in the potential, right? Based on the mass of the tachyon, mass square of the tachyon.
Right.
And then there are higher order corrections.
And you have enough analytic control in string field theory to do this contour integration, or you just don't need to have all the details?
We don't need to do this order, right? Because these corrections are of order G string.
Right.
So they will go into the F and G and so on.
Perfect.
So to leading order, you only need the quadratic part.
I see.
So leading order contour is like the going all the way to the imaginary axis, minus I infinity to infinity. And then these corrections are higher order corrections in GS.
I see. Thank you.
Okay, so now we are going to start to the disk two-point function. So the plan is that I'll try to discuss the disk two-point function in great detail, because that's somewhat simpler, but this also illustrates all the technical issues. And then I'll state the result for the annulus one-point function, okay, which is technically more complicated. Okay, but I'll show you the various pieces of the result that comes. So this two-point function is this. Okay. And you remember that the answer for this that I wrote down was A0, which is the leading order amplitude, product of two disk one-point functions. And then there's a function of omega 1, omega 2. So this contained a finite piece, F finite, omega 1, omega 2. And then there is a divergent piece. So let me write this as F divergent omega 1, omega 2. So this was given by half integral 0 to 1 dy, and then y to the minus 2 plus 2. And this, because it's the divergent integral, we wrote it as AF plus BF omega 1 omega 2. And our goal is to calculate this AF and BF. Okay, so you need to calculate this by making sense of this divergent integral. Okay. So to do that, the first thing we have to do is to understand what this y is in the BRY calculation. Okay, because y, of course, emerged from the BRY calculation. So you have to basically go back and look at what this y is, okay, which particular modulus it corresponds to. So what is y for BRY? Okay. And to understand y, it's best to first map the disk to the upper half plane, because disks are nice to draw, but it's easier to work in the upper half plane. Map disk to upper half plane. Okay. It's just because we are more familiar with the upper half plane. Okay. And that's done by this coordinate transformation. The disk coordinate is related to the upper half coordinate z by this 1 minus iz. Okay. So for example, z equal to I goes to the origin of the disk, z disk equal to 0. This is the unit disk. And z equal to real goes to the boundary. Okay, because you can easily see that if z is real, then the mod of this is 1. So you are at the boundary of the unit disk. Okay. So you are considering two-point functions. So you have to draw the upper half plane and put two vertex operators. Okay. Now, on the upper half plane, we have an Sl2 transformation, and you can make an Sl2 transformation to pick some of the coordinates. Okay. And so what BRY did is the following, that you have these two coordinates, two closed string vertex operators. Okay. So one of them, they put at I. Okay, so one of them they put at I. So that takes away the 2 degrees of freedom, because you are fixing both the real and imaginary part of this vertex operator. So for the other vertex operator, okay, of course you cannot put both of those to whatever you like. Okay. So because you have only one remaining parameter, so they use that one remaining parameter to put the vertex operator on the imaginary axis. Okay. So they put it on the imaginary axis, and the coordinate of this is what they call I times y. Okay. So that defines their y. Okay. And the divergence that we see, divergence comes from y goes to 0. Now you may wonder, what about that means a vertex operator going towards the boundary. You may wonder what about the vertex operators colliding, right? Y goes to 1. So y goes to 1, of course, also has divergence. Y goes to 1 is closed string degeneration. Closed string degeneration, because this corresponds to collision of two closed string vertex operator. Okay. And this could produce divergence. Okay. But those can be treated by analytic continuation, because closed strings do carry energy, okay, and momentum. Okay. So this can be treated by analytic continuation. Okay. And indeed, these are included in a finite. Okay, because they are already defined by analytic continuation. So you don't worry about these divergences, you worry about the divergence as y goes to 0. And this divergence can also be given a physical picture, another physical picture, okay, which is that you had a disk 2-point function, okay, and this divergence can also be described like this, where basically there is a pinch in the disk. Okay. And all the divergences that we'll be talking about, okay, are the ones where there is one narrow neck like this, okay, because this corresponds to open string degeneration. And our goal will be to make sense of these kinds of divergences. So now we have to draw Feynman diagrams. Okay, so maybe I should say one more thing. So you'll imagine, because the closed string divergences are can be handled by analytic continuation, we'll imagine that the closed strings have been integrated out. Closed string degrees of freedom have been integrated out. So essentially, we only draw Feynman diagrams with the internal open strings. So we can ask, how do we draw Feynman diagrams? Okay, what kind of vortices we should use? Okay, and the answer is that you basically use all possible vortices. Okay, all possible vortices, but with this rule, in this particular context, that only internal states are only open strings. Okay. So this Feynman diagram, for example, in this language will be represented. Okay, so this will correspond to a particular Feynman diagram. Okay, the precise connection I'll make a little later. So this kind of degeneration will be associated with the Feynman diagram of the following kind. So I'll draw this. So in my notation, the blue lines will denote closed strings. They're always external lines. Red lines will denote the open strings, internal lines. So essentially the point is that whenever you see a narrow neck, okay, you represent this by open string propagator, and you draw by the two vortices. So this is like a, so you can think of this as an open string propagator connecting to a disk with one closed string. That's this vortex. So this is a closed string open string vortex, and this is another open string connected to a closed string via a disk. So that's another open string closed string vortex. So this will be one of the Feynman diagrams that contribute to the disk 2-point function. And the other Feynman diagram, which is always present, is a contact diagram, which basically in this case corresponds to this one. So essentially the rule of string field theory is that whatever is not included in this diagram, you dump into this. And the point that we'll see later, and I want to emphasize now itself, that all the divergences will come from diagrams like these with internal propagators, because as we discussed, the divergences will come from one of the q parameters going to 0, right? And that requires a propagator. These diagrams will be manifestly finite. Okay, and we'll see this explicitly in as we proceed. Okay, so maybe I should emphasize this here again. Okay. So in my notation, the blue will be closed strings. And red will be open strings.
So yes, Ashok, yesterday you only talk about the string field theory for the open string. So
yes, exactly. So
now,
the closed strings here will be more like a background because they are only in external states.
Okay, so yesterday the free action for the open string is enough to study this one, or
No, it's not enough. We need the interaction. You need the closed open interaction vortex. But I'll describe a way to treat this, which does not require us to explicitly write down the action.
Okay.
So this, of course, so the rules that I'll be giving will come from detailed analysis of string field theory. But once I tell the rules, you can apply them without knowing how it came from string field theory, and that's what I'm planning to do.
Okay.
I'll tell you how to calculate these diagrams systematically without having to write down an action. But for that, I have to tell you the rules of how to translate a diagram like this into an integral over y of the kind that we saw.
I see. Okay.
Okay, so now let me draw the diagrams once more. So then turns out there are three kinds of diagrams that one should write down. One is this one that we have drawn. The other one is the contact diagram. But this diagram, okay, it turns out that it's good to split into two parts. One is the Siegel gauge term, and the other one is the psi1 exchange. So let me explain this. So yesterday, if you recall, we said that the Siegel gauge is not the correct gauge choice for string field theory because the Siegel gauge actually breaks down. Okay. And you should really carry out string field theory in the gauge invariant form. Okay, so you have to ungauge fix, okay. And that required introducing this extra field psi1 in the problem, because psi1, if you remember, psi1 was the one that was multiplying the state 0 on C0 on vacuum, which doesn't satisfy the Siegel gauge condition. So we'll be dividing up the Feynman diagrams into these two classes. One is where you exchange the Siegel gauge state, the other one where you exchange a psi1. Now the Siegel gauge states, okay, have a nice worldsheet description. That's why I have divided into these two parts. Okay. Because if you remember, the kinetic term for the Siegel gauge, okay, was like C0 L0. Okay, the Q became say Q C0 L0 on acting on the Siegel gauge states. So the propagator is proportional to L0 inverse, okay, exactly as we saw, except for some denominators which you don't worry about. Okay. And this we had written as integral 0 to 1 dq q to the L0 minus 1. Okay. So the diagrams where you use Siegel gauge propagator, okay, can be given nice worldsheet interpretation by representing the propagator in this way. Okay. And then we can translate the q's to the moduli variable, the y's, in a way that I'll be describing in a few minutes. And in this language, the y goes to 0, q goes to 0 will correspond to y goes to 0 limit. And again, we'll see this explicitly. It corresponds to y goes to 0 limit. This part has to be calculated explicitly using the psi1 propagator. Okay, we got the action for psi1 yesterday, and we'll have to use the psi1 propagator and the vortices that will appear here to calculate this explicitly. And that also we'll see how to do. Okay. And then this part will be given by integral over some range of y. Okay. But that range will not include any divergent pieces, so you can just do this integral explicitly. So let me now describe the steps that we'll be following. So the step 1 will be to find the relation between y and q. Step 2 is to take the integrals that come from the worldsheet description, which is done in Siegel gauge. Worldsheet always reproduces the result in the Siegel gauge. So take the integrals coming from the worldsheet and express this as integral over Q. So this step is straightforward once you have done that step one, finding the relationship between Y and Q. Then step 3 is that if we take integral of this, if we get an integral of this kind, dq q to the minus beta minus 1, okay, we interpret this as coming from L0 equal to minus beta state and replace it by 1 over L0, which is minus 1 over beta in this case. Okay, because we have seen that that's where 1 over L0, when you try to represent for negative L0, you get divergences. Step 4 is to deal with the logarithmic divergences. So step 4 is that integrals of the form integral 0 to 1 dq q inverse, these come from 0 modes, from L0 equal to 0 states, which could be collective mode or ghosts. Now, at tree level, that we are, I mean, for this 2-point function, you only work at tree level, so the ghosts are not there. Okay. But it doesn't matter, I'm giving the general rule. Okay. So the general rule, as we have seen, that the ghosts, if there are ghosts of L0 equal to 0, right, then you know that those are actually not there because you shouldn't use a gauge fixed version. So you remove the ghost contribution, and the price you pay is that you have to include expression as psi 1. Okay, which you have to write separately. For the collective modes of course physical. Okay, it's not that we are throwing them away, but you know that we shouldn't treat the collective modes by Feynman diagrams. Okay. These are to be integrated at the end. Okay, so the ghosts are removed. So these have to be integrated at the end and not via Feynman diagrams. N and not via Feynman diagrams. So net result is irrespective of whether it's coming from the collective modes or the ghosts, is to basically remove contributions of this form. Involving integral 0 to 1 dq q inverse. Okay, with the understanding that they are taken care of separately. Okay, and you have seen what they do. So this is the procedure that we are going to follow. And we are going to start with step 1, namely find the relationship between Y and Q. Okay, and I'll describe how exactly to do that. So step 1, relation between Y and Q. So let me draw the diagram again. So here you see that these two are on shell. This is on shell. This is on shell. But this is off shell. Because this is internal line. In general, this can be off shell. So now let's see how we define this vortex. So what is it after all? This is a disk 2-point function. These 2-point function are one closed string, one open string. Okay. So by mapping the disk to the upper half plane, okay, we have to write this as some kind of 2-point function of a closed string and an open string. Okay. And now because we have one closed string and one open string, so the open string vertex operators are always on the boundary. Okay. So then by Sl2 invariance, you can always put the closed string at I, as BRY did for the first vortex, and the open string, which is lying on the real axis, okay, that's one parameter. So remaining parameter of Sl2 can be used to set that equal to 0, the origin. Okay, so this is the closed string, this is the open string. So there is no ambiguity, there is no freedom in choosing where to put the open string and where to put the closed string. Okay, that's fixed. The freedom exists in defining what coordinate system you use to insert these. Okay, and I'll explain what this means. Now, closed strings are on shell. That means these are dimension 0 primaries. For dimension 0 primaries, it doesn't matter. It's invariant under reparametrization on a coordinate transformation. So whichever coordinates you use, you get the same result. Okay, so it doesn't matter what coordinate system you use here. This, however, requires the choice of a coordinate system if O is off shell in general. So we introduce what is called local coordinates. We need a local coordinate, need to specify, a local coordinate W at the open string. Okay, this is the coordinate system in which it's inserted. So if Z is the coordinate on upper half plane, then in general W is related to Z by some functional relationship. Okay, or Z is the inverse function. And this means that if take a open string, off shell open string, okay, let's imagine that it's you have an open string with vertex operator V, okay, which is not necessarily dimension 0 primary because it's off shell. Then what one should insert at this stage, at this point, is not V at 0, but you have to first conformally transform V by this conformal transformation F, and you insert that at 0. So let me give some example. That should make it clear. Suppose the vertex operator, suppose V is C. So this is the dimension -1 primary. Then F dot V, okay, at, let's say, take any point W, then you'll set W equal to 0. This is given by F prime of W inverse C of F of W. Okay, that's what I mean by you are conformally transforming C, and this -1 reflects the fact that it's a dimension -1 primary. So F dot V of W of 0 will be F prime of 0 inverse times C of 0. And I should say that it's a normal convention that W equal to 0 corresponds to the location of the puncture, corresponds to the location of the vertex operator. So if in the Z plane we are inserting the vertex operator at Z equal to 0, okay, that we can always achieve by Sl2, then W equal to 0 should map to Z equal to 0. Okay, which basically means that F of 0 should be 0. Okay, otherwise f is arbitrary. Different choices of f will correspond to different looking string field theories. Okay, but let me first give another example. Okay. Suppose v is derivative of c. Then if we take this, okay, so this derivative with respect to w, I can write this as del w f of cw, okay, because f is like a similarity transformation of c by some abstract operators involving the Virasoro generators, right? W is just a label, so you can take this derivative out. So this is derivative of f prime of w inverse c of f of w. Too many brackets, let me. So this will be given by first the derivative of this, so that's minus f double prime of w over f prime of w squared times c of f of w, and then plus when the derivative acts on this by chain rule, okay, you get out a factor of f prime of w, so that I'll write as del c of f of w, okay, where this means the derivative with respect to the argument of c. So this is the way we can figure out what you should insert, okay, but the choice of f is important. So different choice of f gives different string field theory. Okay, so then you may wonder that then which one should you use? But there is a general result, okay, that was due to Hatta and Zweiberg, that was in the early days of in the 90s, which showed that these different choices, these different SFTs are related by field definition. Which means that the intermediate results may depend on the choice of f, but the physical results, physical quantities should be independent of this choice. Okay, because field definition cannot change anything.
Can I ask something? These f's should be maps from the upper half plane to the upper half plane?
No, not necessarily. Okay, maybe I should emphasize this. So the only thing that we demand is that f of w should map a neighborhood of w equal to 0 of w equal to 0 to the z plane in one-to-one fashion. Which basically means that f should have a Taylor series expansion with a finite radius of convergence. But we are not demanding that f maps the upper half plane to upper half plane. Although the maps that we'll be working with will have that property because it makes life much simpler. Okay, but it's certainly not necessary. This proof is valid for any choice of f that has this property, that it should a neighborhood of w equal to 0 should be mapped to some region in the z plane in the one-to-one fashion. And the reason for this demand is that we need, not here you saw that we needed the second derivative of f, right? In general, if you take a highly complicated conformal operator, then you'll have multiple derivatives of f. So you have to make sure that any finite number of derivatives of f is well defined at w equal to 0. Okay, so that you demand, but not that it maps upper half plane to upper half plane. So it's not an Sl2 map in general. Is this okay?
Yeah, thank you. I guess then you are, so in this map, you're mapping the open string field in a little region around the origin to the upper half plane in which you're going to compute the correlator.
Exactly. That's
okay. So you just need that region to define the state.
exactly.
Okay,
yeah.
Thank you.
Okay, so now let's come back to this diagram. Okay. So here again, I'll state the result of string field theory without actually proving it. Okay, but this result is nice and geometric, and it's easy to appreciate what this result tells us. So here is a single gauge state. Okay. So this is a standard propagator, so it has a Q parameter with it. Okay. So as we said that this should correspond to some region of the Y integral. Because every Feynman diagram is supposed to cover some region of the Y integral. Okay, every Feynman diagram in the single gauge. Okay. The psi exchanges have to be computed separately. Okay, where every Feynman diagram in the single gauge is supposed to cover some region of the Y integral. Okay. So you can ask that which region of Y integral does it cover? Which region of Y integral does it cover? Does this diagram cover? Okay. And the answer that string field theory gives is the following. So you see that you have two vortices, two open closed string vortex. So you can introduce two upper half planes, right? This associated with this vortex, there is an upper half plane where the closed string is inserted at I and the open string is inserted at 0. Associated with this, there's an upper half plane, closed string at I, open string at 0. So let's call the corresponding upper half plane coordinates Z and the associated local coordinate W. And here we call this Z prime and W prime, the local coordinate as W prime. So we have Z equal to f of W and Z prime equal to f of W prime. Okay, and you can also invert the relation. Namely, W is equal to f of Z. Okay, again locally near that neighborhood, and W prime equal to f of Z prime. Now the result of string field theory is that we identify Z and Z prime planes using the relation W prime equal to minus Q. So Q is the same parameter Q, okay, the swinger parameter of the propagator. So what this does, okay, is it says that W prime is a function of W. It's not an independent coordinate anymore. Okay. And by going through this, this means that Z prime is a function of Z. It's not an independent coordinate anymore. Okay. So this identification basically glues the two upper half planes into a single upper half plane. And in that single upper half plane, wherever the vertex operators go, that's the location of the closed string vertex operators. And then you have to do some manipulation, some Sl2 transformation again to bring it to the form I and I times something. And that something is what we'll call Y. Again, let me give an example. I think that it will become clear. So let's take a simple example. Okay, and in fact, that's the vertex I'm going to use for the actual calculation. Okay, and then we'll see some generalization. So let's suppose you take W equal to lambda Z. Okay, where lambda is some constant. Then once you have chosen this, of course, you have to choose the same vertex on both sides, right? You have no choice because it's the same string field theory after all, right? I mean, you cannot use different vertices for one particular calculation. You fix your all vertices once and for all, and then you start doing a calculation. So W prime equal to lambda Z prime. So W prime equal to minus Q translates to lambda square Z prime equal to minus Q. Okay. So we see that z prime and z are not independent coordinate. They are related by a functional relationship. So now let's see where are the vertex operators. So the vertex, the closed string vertex operators, the open strings have gone, they are internal lines. So the closed string vertex operators are at the position z equal to I. Okay, so let's use the z coordinate. Okay, you could also use z prime, but let's use the z coordinate. And z prime equal to I. Okay, this translates, if you look at this translates to z equal to I times q by lambda square. So in the upper half plane, the vertex operators are at I and iq by lambda square. So if you compare that with the BRY parameterization, I and IY, we see that by comparing these, we get the relationship between y and q, y equal to q over lambda square. So this determines the relationship between y and q. Okay? In this case, it's very simple. Okay, almost no calculation needs to be done to find the relationship between y and q. Is this clear?
Yes, this is clear, but I have one question with that identification. The like for example, omega times omega prime equal minus q.
Yes. Okay.
Is it unique way to identify to plane or?
Well, it's not unique, but string field theory gives you this. Okay, if you look at the single gauge propagator, right, which is like 1 over L0, right? Okay, but 1 over L0 you are representing as dq q to the L0 minus 1.
Yes.
So now if you take the matrix element between two states, so 1 over L0 n, this is like integral dq, okay, and the matrix element of q to the L0 minus 1 between m and n.
Yes.
Okay. So basically what it does is that it takes the state n, translates it, or not translates, scales it by this q. Okay, that's why this q factor, because L0 is a scaling operator, right?
Yes.
And then this is the what is called a Vpg conjugation, which is like inversion. Okay, z goes to minus 1 over z. And that's what you see here.
I see. Okay.
The z, so this gives you z equal to, sorry, w equal to, sorry, not w, z, w, because this is done in the w coordinate system. So this gives you w equal to minus q over w prime, right? So this is basically a combination of scaling and inversion. The scaling comes from this q to the L0 and the inversion comes because of this Vpg conjugation.
Okay.
But if you go through it, that this is what in string theory calculation translates to. And that's why single gauge is important, because it's 1 over L0 is a propagator in the single gauge.
I see.
If you use another gauge, then there will be a different swing relation.
Oh, I see. So this relation really coming from the gauge.
Exactly.
Okay.
This is that if you fix in the single gauge, then this you get this.
Okay.
So as long as you are including these sum over states, only single gauge states, then this procedure is correct. Okay. And that's why this describes, okay, I'll draw the diagram. So that's why this describes only these class of diagrams. The single gauge states, right? The psi one you have to keep separately.
Okay.
So this, then we see that this, for this diagram, okay, we have this relation q or y equal to q by lambda square. So then the range 0 less than or equal to, sorry, 0 less than or equal to q less than or equal to 1. Okay. This corresponds to a range 0 less than or equal to y less than or equal to 1 over lambda square. So the rest of the region, y between 1 and lambda square, okay, is covered by the rest of the diagrams. Okay, that's the definition of the vertex. This vertex now has to cover the region 1 over lambda square less than or equal to y less than or equal to 1. The other diagram cannot be treated this way, right? Because this correspondence between world sheet and the string field theory Feynman diagrams work only for the single gauge states. So this diagram has to be calculated separately. And that we'll do later. So this has to be analyzed separately.
So lambda has to be bigger than 1?
Well, if lambda is not bigger than 1, suppose lambda is less than 1, then you basically have to subtract this contribution. So then by in the definition of the vertex, you subtract it, which is perfectly consistent, but it's not very convenient. So normally you take lambda to be bigger than 1.
I see. In BRY, there was also a contribution from y going to infinity, or?
No, there is a contribution for y goes to infinity, because what happens is the following, that on the upper half plane, if you look at this upper half plane, there is a I and IY. This is what you took, right? Mm-hmm. So if you take y to be larger than 1, right, which means it's on this side, this can be brought back to y less than 1 by z goes to minus 1 over z, which is an Sl2 transformation.
I see.
So you only cover the range from 0 to 1.
Right. Thank you.
Okay. Any other question? Okay. So now we are ready to carry out this divergent integral. So we have this half integral 0 to 1 dy y to the minus 2 plus 2 omega 1 omega 2 y inverse, right? This is the integral you have to do. So the first thing you do is to now divide up into two parts, okay, which corresponds to these two different Feynman diagrams. So one is from 1 to 0 to 1 over lambda square. This is dy y to the minus 2 plus 2 omega 1 omega 2 y inverse plus integrals 1 over lambda square to 1 dy y to the minus 2 plus 2 omega 1 omega 2 y inverse. Okay. So let's do this part of the calculation first. Okay, this is finite integral. So this gives you, there is a half, sorry, half I forgot. Yeah. So this gives you half of this integral is lambda square minus 1 plus 2 omega 1 omega 2 log lambda square. So this is the divergent integral. Okay, so for this you first change variable y equal to q by lambda square. Okay, and write this in terms of q. So in that language, this becomes half integral 0 to 1 dq. dy y to the minus 2 becomes lambda square dq q to the minus 2. So lambda square dq q to the minus 2 plus 2 omega 1 omega 2 q inverse. And now you follow the rules that we had given earlier. You see this is like q to the power minus 1. So that's like coming from an L0 equal to minus 1 state that you can recognize as the tachyon intermediate state. And so the rule that you had given is to replace this integral like this, integral 0 to 1 dq q inverse q to the minus 2 by minus 1. So the first thing is lambda square times minus 1. This one is coming from the L0 equal to 0 state. And as we said, the L0 equal to 0 states cannot be treated by Feynman diagrams. They are treated separately, differently. Okay. Like in this case, it's coming solely from the collective coordinate. But that integral, of course, we will do at the end anyway to recover the delta function, the energy conserving delta function. So that this is not part of that integral. So we replace this by 0. Okay. Anytime you have dq q inverse, you replace it by 0. And now you just add these two. Okay, we add these two. The lambda square part cancels. And what you get is half times minus 1 plus 2 omega 1 omega 2 log lambda square. Okay, so you'll keep this in mind because you have to calculate the third diagram and then add to this. Is this clear so far?
Yes, it's clear.
Okay, so string field theory gave us this. So third diagram in this case, in fact, is easy because this diagram is this, right? Psi 1. So you have to calculate this 2-point function, right? And what you will see is that this 2-point function is 0. So this 2-point function is basically the 2-point function of a vertex operator, closed string vertex operator I, okay, where you insert the closed string vertex operator. Now let me write it explicitly: C bar times the matter part. Okay, this is the matter part of the tachyon vertex operator. And here you have the open string vertex operator psi 1. Okay, so psi 1 multiplies, remember, psi 1 multiplies C0 on the vacuum. Okay. And the vertex operator associated, so this is like del C of 0 in the vacuum. So the vertex operator for C is C0 is del C. So here what you insert is F dot del C. But this you had already computed, right? This was del C of 0 minus F double prime of 0 over F prime of 0 square times C of 0. Now here we have taken Z W equal to lambda Z, W equal to lambda Z. So Z equal to W over lambda. Okay, and this is what we had called F of W. So you see that F prime of W is 1 over lambda, but F double prime of W is 0. Okay. So this term is 0, so this just gives you del C of 0. So what you have to compute is the C bar. So you have to calculate this C bar Vt at I and del C at 0. These are on the upper half plane. But this you can relate to a computation in the full complex plane, okay, by what is called the doubling trick. So doubling trick basically tells us that whenever you have a C bar, you replace it by C by put it at the complex conjugate point and calculate the correlation function in the complex plane. Okay, so this is proportional to C of I, C of minus I. Okay, we replace, as I said, C bar by C, but change the argument from I to minus I and del C of 0. This is on the plane now. And this is actually 0. Okay, so let me just show that this is 0. So C of I, C of minus I, C of Z on the plane. Okay, if you remember the formula, it's basically product over I Zi minus Zj. Okay, so this is proportional to Z minus I times Z plus I times I minus I, so I plus I. So that's 2I times Z square plus 1. So if you take C of I, C of minus I, del C of Z, that's 2I times 2Z. So if you set Z equal to 0, this just vanishes. Okay. So that basically shows that this diagram is actually 0 here. Is 0. Okay. So then the total contribution is basically what we had found here. Okay, so I'm going to write down total contribution is this one. So F divergent is half times -1 plus 2 omega 1 omega 2 log lambda square. And remember that we had identified this as AF plus BF omega 1 omega 2. So this gives you AF equal to -half and BF equal to log lambda square. So AF equal to -half is an answer which you had seen in the first lecture. This is what one of the results I quoted, and this agrees perfectly with the BRY calculation by comparison to the matrix model, right? Because they got 0.50 minus 0.50 plus minus 0.01. Now BF, you see, depends on lambda, right? But at the end, physical results shouldn't depend on lambda, right? Because lambda is part of the choice data that went into the choice of coordinate system, the local coordinates W. So BF depends on lambda. But fortunately, BF, as we had seen on the first day, BF never enters the expression for the S matrix. What enters the expression for the S matrix is this combination BF minus 2BG. BF minus 2BG. So you have to calculate BG, okay, which came from the annulus one-point function. And this we will find is indeed independent of lambda, it's just log 4. Okay, this is the result I quoted earlier. So you'll get the 2BG will be log of lambda square by 4, and when you subtract, you'll get this log 4. So this is a consistency check that at the end, nothing should depend on lambda or any of the parameters that we introduce in the calculation. Okay, are there questions? Okay, now let me do a slightly general thing. Okay, because I want to illustrate everything in terms of this two-point function, because annulus is just more complicated version of this kind of analysis. Okay, so that I'll just quote the results. So let's ask, what if we had chosen a different f of z? A different f of w. Now, as I said, in principle, you can take f of w to be any function that is analytic near the origin and gives a one-to-one map between w and z plane. But the calculations are infinitely simpler if you choose this to be Sl2 family. And the reason is that if we don't choose them to be Sl2 family, then what happens is that after you glue the z prime plane and z plane together, you will find that the z plane doesn't have the shape of an upper half plane. Okay, it gets a complicated shape because there are branch cuts in that process. So the boundary doesn't lie on the real z axis. There is still, nevertheless, a theorem which tells us that there is a way to make a coordinate change from z to something else, which brings it back to upper half plane. Okay, that's what is called the uniformization theorem. But that change of coordinate is complicated to determine. So this complication doesn't arise for the Sl2 family of maps, and that's what we'll restrict. Okay, Sl2 family of maps, just for convenience. Okay, not that the results will be different. Okay, well, at least we don't expect the results to be different, even though it has not been the explicit calculation has not been done for this case. Okay, but the general arguments into Hatta and Zoibach, which says that it shouldn't be different. So we'll take the relation between w and z to be w equal to lambda z over, say, 1 plus gamma z. Okay, we just added this new parameter gamma. Okay, it's still Sl2. And the inverse relation is z equal to w over lambda minus gamma w. Okay, which is what we had called f of w. So in this case, if we draw this diagram, then it will again correspond to w prime equal to minus q. But this is now complicated because we'll have lambda squared z prime over 1 plus gamma z prime equal to minus q. Okay. You see, it can still you can still solve it because this equation is a linear in z, right, and linear in z prime. So you can solve for z prime in terms of z or z in terms of z prime in a one-to-one fashion. But it's of course a little more complicated than what we had done earlier. So the vertex operators are at z equal to I and z prime equal to I. Okay, so you can substitute z prime equal to I here and solve for z. Okay. So that corresponds to some z. Okay, let's call this z equal to z2. Okay, the second vertex operator is inserted at z2. Okay, I'll not do these explicit calculations, but I'll give the steps so that you can actually complete this if you want. Okay. So you can find z2 explicitly. Okay. But in general, what you will find, real part of z2 is not 0. Okay, so z2 is not on the imaginary axis, so you cannot directly compare with bry because bry are taken to be I and iy. So you have to do a little more work. So introduce a new coordinate system. Introduce new coordinates. Z tilde. And I'll take Z tilde again to be related to Z by Sl2R, but a particular kind of Sl2R. Okay, so A is some real number. Now, this particular class of Sl2R has the property that Z equal to I gets mapped to Z tilde equal to I. Okay, you can easily verify this. Set Z equal to I for any A, any real A, Z tilde you get is I. And Z equal to Z2, okay, this will map to Z tilde 2, which is Z2 minus A over 1 plus AZ. Okay, Z2 of course is known. And now the idea is that we adjust A so that real part of Z2 tilde is 0. So in the Z2 tilde plane, the vertex operators, one of them is at I, the other one is on the imaginary axis. And so whatever you get, so this solves A, this determines A. Okay, this determines A uniquely. And then whatever is you get for imaginary Z2, we define this to be Y equal to Y. This defines Y. So at the end of all this, what it does is that it gives Y as function of Q. Right? Well, after all, you started with Q, right? Q entered this formula over here. Okay, lambda and gamma are just constants. So Y Q entered this formula. So you ultimately, by doing all this, you again get Y as function of Q. And then you can ask, what does this range correspond to? This will correspond to Y in some range. Okay, so this is determined now. And again, as before, you declared that this diagram, this single gauge diagram, this covers the range 0 less than or equal to Y, 0 less than or equal to Y naught. And then the other diagram, this covers Y naught, Y between Y naught and 1. And then you proceed as follows. Okay, as before. Okay, so let me say what to do. So you take this integral half integral 0 to 1 dy y to the minus 2 plus 2 omega 1 omega 2 y inverse. So this you split into two parts. One is from 0 to y0, dy y to the minus 2. And here you change variable to q. And basically you will end up with half integral 0 to 1 dq. Okay. In fact, the first terms are the same, lambda square q to the minus 2. Then you get 2 omega 1 omega 2 q inverse plus finite terms, order q0 and higher. Okay, these give finite results, which you can do explicitly. And here again, we replace this by half times minus lambda square. This term you drop. And then these integrals, if there is anything left, the finite integrals, you can do this. And then you just add this to this to get the total answer. So the algorithm is quite straightforward, and I'll give the result that one gets from here. So the result that we will get, okay, and if you are willing to do the calculation, you should be able to verify this. That we get a result gamma squared after adding minus half something is wrong, minus half plus omega 1 omega 2 log lambda square. So you see that this is extra. This is extra term beyond what we had gotten earlier. So you may wonder what's going on. But of course, you have to remember that there's a third diagram. There is a third diagram here. Okay, and you have to now recalculate this and see what you get. So in this case, you have this relation z equal to w over lambda minus gamma times w, okay, which you had called f of w. You can easily check that f double prime of 0 is not 0 anymore. So f double prime of 0 is not 0 anymore. Okay, you can calculate what it is. And in particular, f dot del c of w, or del c of 0. Remember the formula, we had del c of 0, okay, because w equal to 0 goes to z equal to 0, minus f double prime of 0 over f prime of 0 square times c of 0. This turns out to be 2 gamma. So this quantity you can easily calculate is 2 gamma. So what you have is del c of 0 minus 2 gamma c of 0. So this is what you have to now insert at the origin. So if you look at the upper half plane, this is for this particular 2-point function calculation, where this is psi 1. So in the upper half plane, you insert, as before, c bar vt. But here, you now insert del c of 0, this is at I. Here you insert del c of 0 minus 2 gamma c of 0. Okay. So this part gives you 0 as before, but this part doesn't. This part in general is a non-zero result. So this diagram is not zero anymore. Okay, so this diagram is not zero anymore. Okay, and the question is, what is it? So in principle, you can normalize it correctly, calculate these individual vortices, okay, and put the psi1 propagator and calculate it. But what I'll describe now is a shortcut to doing this. And the shortcut is the following. So we calculated this. Let's compare this with another 2-point function. Okay, suppose we had the same closed string, but here instead of the psi1, we had a psi0. So psi0 vortex operator, remember the psi0 multiplies C1 on the vacuum. Okay, so the vortex operator for this is just C. Okay, this is C of 0 on the vacuum. Okay. So if you are doing this calculation, okay, then what you insert here is C bar Vt of I, and here you will insert f dot C of 0, which is f prime of 0 inverse times C of f of 0. And in this case, f prime of 0 inverse, this is basically lambda times C of 0. Okay, it will become clear soon why we are doing this. So let's compare this diagram with this diagram. Okay. So this one doesn't contribute anyway, right? Del C of 0 doesn't contribute anyway. So what we see from here, if you call this psi0, okay. So maybe I go to the next slide. At this stage, we are still calculating psi1, right? Okay, I think this formula are not too complicated so that you may remember. So we are comparing the ratio of two things, okay? This divided by another diagram. And so the point is that this is psi1, this is psi0. So what is the difference? First of all, the vortices are different. So the vortices, the ratio of the vortices is 2 gamma over lambda. Okay, this gave 2 gamma and this gave lambda. And because there are 2 of these vortices, they 2 gamma over lambda square. And then you have the psi1 propagator over psi0 propagator. Okay, that's the ratio of these two. The reason that we are calculating this is because this is already known, as you'll see in a few minutes. Now, psi1 propagator versus psi0 propagator, right? This also you know, okay, from what we discussed yesterday, because remember the action, okay, the action had half psi0 square plus psi1 square. And because the propagator is the inverse of the kinetic operator, this shows that this ratio over here is actually half. Okay, because of the psi1 square having twice the coefficient as of the psi0 square. Now let's ask, what is this object? Psi0. This is the contribution from the tachyon exchange diagram. But if you just go back a few slides, you see that this contribution is precisely the tachyon exchange contribution. Q to the minus 2 is coming because there is an intermediate tachyon state. So you have already determined the tachyon exchange contribution, that is minus half lambda square. So you are going to put that in. So this is minus half lambda square. This is minus half lambda square. And now just put everything together. So the net result, okay, let me first find a box so that it doesn't get confused with other things. So net result for this object is now 4 gamma square over lambda square times a half from this ratio times minus lambda square by 2. That's minus gamma square. And this precisely cancels that extra term that we had. This precisely cancels this term. So the sum becomes what you had earlier. The result doesn't change. And that is good because after all, nothing should depend on the choice of this local coordinates, right? Particularly AF is directly appears in the S matrix. Okay? So it better be that AF doesn't change. Okay, and indeed it doesn't change because gamma square gets cancelled by the extra diagonal. Are there questions on this? Okay, so in the few minutes that I have, okay, I'll now describe the results for the annulus one-point function. And so there, we are going to, I'm going to use the slide. Okay, I hope the slides are visible. Close this.
Yes, it's visible. And is it related to this AG and the BG calculation?
Yes, exactly. This will be related to the AG and BG calculation, right? Because G omega had the AG and BG.
I see. Okay, yeah.
Okay. So G omega, okay, was given by a finite piece and a divergent piece. So the divergent part of G is given here. Okay, this is what we had written down earlier. The BRY calculation gave you this. Now to proceed as before, okay, we have to understand where this, what the V's and X's are. Okay. And so that of course can be read out from the BRY analysis, right? What they call V and what they call X, because that is needed because you want to make connection with the Q's. So what BRY used is that they took this picture of the annulus, they take a rectangle, the width is fixed to be pi, and the length of the rectangle take to be log of V inverse. Okay, that's what defines V. So V goes to 0 correspond to a long rectangle. And then we identify the left and the right edges. Okay, that's what makes it into an annulus. Sorry, I think, yeah. Identify the left. I should have called it actually log V. It doesn't matter. V equals to V inverse. It doesn't matter. It's okay. So identify the left and the right edges. And 2 pi x is the distance of the vertex operator from one of the edges. Okay, that is the x goes to half minus x symmetry, so it doesn't matter from which edge. Okay, so that's 2 pi x. So once you understand the geometry, then you follow exactly the same procedure to identify the relationship between the v's and x's and the q's. It turns out that the actual one-point function annulus comes from several sources. So let me describe those. The first are the string field theory Feynman diagrams with Siegel gauge states. And in that calculation, you have to remove the zero modes as before. Okay, and this time the zero modes will include both the ghosts as well as the collective modes. Okay. But it's understood that whenever you have a DQ-Q inverse, you just remove them. And so these are the various Feynman diagrams that you have to deal with. Okay, again, as before it's a one-point function, so there's only one external closed string. All internal lines are open strings. Okay, because internal closed strings have already been integrated out. And this, for example, is a contact interaction. This means there's a one-point function of open string on the annulus. Okay, but this is a finite. The range of v and x is finite for this. And similarly, you have these diagrams. And in each of these,
all the red line is just open, like there
all the
is
red lines are open. Exactly.
Okay.
Yes. So all the red lines are open strings.
For this, you need like a 3 vertex of
Exactly. So you have to build the 3 vertex. Right? Again, there is a choice of what you take to be the 3 vertex. But once you take the 3 vertex, then things start getting determined. It's not that just like that once, if you go back to this picture over here, okay, maybe I can draw this here. You see, for the 2 vertex, this had this freedom of choosing f of omega, right?
Yes.
But once f of omega is fixed, then this one gets fixed. What range of y covers this is not arbitrary anymore. So it's not that each vertex can be chosen independently. There are interrelations between these vertices. But of course, there's a lot of freedom. And when you write down the answers of the various parts, you will see all this freedom, the various parameters and functions that enter in the construction of these vertices. And as I have also said that I'll be, the way I did the analysis, I use specifically the Sl2 classes of vertices because analysis becomes infinitely simpler for those. But in general, the general arguments show that it doesn't matter what vertex you use, you should always get the same result as long as they are all internally consistent. And the internal consistency here basically means this consistency between the choice of f here and the consistency of the range of y integral that you use for this vertex. Is this clear?
Yes.
But otherwise, you are certainly right that you have to include this vertex, right? You have to specify the local coordinates. So this is like this 3-point function, right? So you can think of this as an upper half plane with 3 insertions. The 3 points can be fixed at 0, 1, and infinity, or anywhere else you like. But what local coordinates you use is up to you. You have to specify them. Usually, it's useful to specify the local coordinates so that under cyclic permutation, one goes to the other. Okay, but that's not necessary. Otherwise, you have to symmetrize. But with those constants, you can figure out what class of local coordinates is the most convenient class to use. So indeed, you have to fix all of those. Okay, so in this example, let's see where. Oops. Okay, let me open this empty. Yeah. So in this example, here you need, for example, the 3-point vertex, right? Here it's 1 closed string and 2 open string, right? So that vertex also you have to specify, and so on. So this is one class of diagram. This is what you have already seen, and the idea of evaluating this is simple. You take this expression over here, then find the relation between v and x and the q parameters, express them in terms of q's, and then apply the rule that we get here, right? dq q to the -2 replaced by -1, dq q inverse terms you just throw away because those are 0 modes. Then you have to include diagrams like this, okay, a psi1. Okay. You see, any of these could be psi1. Okay. But because of this property that I said, that for the initial choice of vertex that I gave, okay, and that's the vertex I use for the open closed, psi1 here gives you 0 because the vertex between 1 closed and 1 psi1 is 0, as you have seen. So psi1 cannot be here or here. Okay, this can be psi1 or this can be psi1, and those are the 2 diagrams I've drawn here. Okay? This can be psi1 or that can be psi1. So these diagrams have to be computed explicitly by using similar trick. Okay, in fact, here also it turns out the easiest that you compare this with the one where you replace psi1 by psi0, because that's already computed from some other diagram, and then you calculate the ratio, okay, which is given in terms of the ratio of the psi1 propagator to psi0 propagator. Now there are 2 other contributions that also have to be included. So one is the relationship between you remember that you have the field phi. that is the collective mode, and that is the mode that comes from the open string that multiplies C1 alpha minus 1 0, and the collective coordinate phi tilde. And yesterday we wrote down this relation, phi equal to 1 over pi root 2 G open times phi tilde. It turns out that this relation also gets corrected to higher order. And maybe I just show one reason why that correction comes. Okay, let me, because it's important. So yesterday, remember, I drew this picture, and I said that, okay, we have an open string vertex operator inserted here, I root to del x. And if we have a bunch of closed string vertex operators, okay, of energy I omega 1 x e to the I omega 2 x, etc., then you can do this integral, okay, pick up the residues, okay, and this diagram should be proportional to I times omega 1 plus omega 2. Okay. And you compare that, so the coefficient of proportionality, you can compare with what you expect, okay, because the expected coupling of phi tilde, is I times precisely minus I times omega 1 plus omega 2 plus etc. times phi tilde. Okay. So you compare this coupling, okay, so this is multiplied by phi, this coupling with this coupling, and that gives the relation between phi and phi tilde, okay, a constant. But what happens here, that when you actually do this calculation, okay, you are not only integrating over this, okay, we are also integrating over the coordinates of this. Okay. And there can be divergences where this vertex operator and this vertex operators comes close. Okay. Divergences where one of the vertex operator you can fix at the origin, but one of the closed string vertex operators and this open string vertex operator that is here, okay, when they come close, there can be divergences. Okay. And this also has to be treated by using a string field theory. This has to be treated using SFT. Okay. And what one finds is that this simple argument that it is always proportional to I omega 1 plus omega 2, and hence the relationship between phi and phi tilde is just a constant multiplicative factor, that actually breaks down. Okay. But the amount of breakdown you can figure out by doing this detailed comparison. Okay, you can calculate this diagram, regulate all the divergences using string field theory, get finite answer, and compare with what you expected. Okay. And that modifies the relationship between phi and phi tilde to higher order. To order G string to the 0, of course, there's no modification. Okay. But at order G string, there is a modification. Okay. So the precise relation between phi and phi tilde gets modification, where this is a computable function, okay, which you can compute using the string field theory techniques. Okay. But this means that when you convert this d phi to d phi tilde, okay, you have an extra multiplicative factor which you can exponentiate, and this gives a new one-point function of the closed string tachyon, okay, proportional to a of omega. Okay, this is a computable function, but this gives you a new contribution to the one-point function. Okay. So this also has to be added to G, okay, because this contribution is not included in the worldsheet analysis. Okay. So we'll call this G Jacobian. Okay, this one we call G of psi 1. Okay, this one was G worldsheet. Okay, this is a direct regularization of the worldsheet analysis. Okay. And then it turns out there is a similar Jacobian coming from the relationship between theta and theta tilde. Okay. Yesterday we wrote down the simple relation, but again detailed analysis taking care of all the divergences, so that this also gets modified by a term proportional to phi, the closed string tachyon vertex operator, tachyon field. Okay. And this is again a computable function, v of omega. Okay. So this gives you a new contribution to the G of omega, which you can call G gauge. Okay. And now here I give the results for these different components. Okay. So you see that various things have appeared. Lambda tilde, okay, is a new parameter, okay, just like lambda. Okay, this in fact enters the construction of the 3-point vortex, the open string 3-point vortex that you just mentioned. Then h of beta is a new function. Okay, this also enters the construction of the string vortex. Maybe I can just say where that comes from. Okay. So h of beta basically comes from having to describe this vortex. Okay. One closed string, two open string, right? This was also one of the vortices that was in the Feynman diagram. And when you represent it in the upper half plane, you can represent it by a closed string at I. And the open strings, you can put them symmetrically. One parameter you can fix, but you can fix it as minus beta and beta. And then this h of beta that we saw, that function. So h of beta enters inside the relation z equal to f of w. You see, now f of w has to be specified for each beta separately. So you can not only introduce a parameter, you can introduce a whole set of functions. Okay, and that's what that's why h of beta enters. So this h that you see here is from there. So in any case, these are complicated formulae. Okay. But the important point is that after you add all that, everything cancels. Okay, and that's in fact one of the key consistency checks of this whole analysis. That if you had made a mistake, right, these dependencies or these extra parameters wouldn't cancel. After you add everything, it cancels and you arrive at this expression for the divergent part of G. And this is where this AG and BG come from. Okay, you can see that BG is just half log lambda square. BG is, sorry, what happened here? I think I missed a half somewhere. This, oh yeah, that's fine. This should have been there should have been a half here. BG should have been a half log lambda square by 4. But when you calculate BF minus 2 BG, that's the combination that enters the S matrix. You just get log 4. So that more or less describes the calculation of the annulus. Okay, of course, the actual calculation is quite involved. Okay, but the general principles are exactly the ones that I've outlined for the these two-point function. Okay, so I think that's more or less the end of my talk, and I'll just like make some final remarks. Okay, maybe I'll just put them up as a slide and then pause for questions. Okay. Okay, so that's the end of my talk. Are there questions?
I guess D-instanton is never an object can see in low energy effective theory. I mean, space-time effective theory.
Okay, see, Green and Gutperle actually constructed a D-instanton solution in type 2 supergravity. It's a little singular.
It is singular, yes. That's
yeah.
Right.
Well, you can, just like all D-branes are somewhat singular solutions, right?
So I guess I was trying to ask, is this issue of divergence and then cure thereof has an image in space-time field theory, even if it's approximate, say space-time gravity?
Yeah, I mean, the problem is that in space-time, from the space-time viewpoint, it's not even clear how to start doing these calculations.
Right.
Because from the supergravity, if you start doing loops, it's divergent from the beginning, right?
Right.
So you need string theory to regulate the UV divergences. Here, what you are seeing, of course, are infrared divergences, so they are not UV. But nevertheless, the fact that there is a tachyonic mode which you can treat by steepest descent contour, these are very hard to see from supergravity.
Right.
So I think one needs the worldsheet picture to do any serious calculation involving D-instantons. Just like other D-branes, right? I mean, you can try to describe D-branes as classical solutions, but the actual rigorous calculations really uses the worldsheet description.
Yeah, I was just wondering aloud. I mean, of course, once you have gravity in the path integral, there are all kinds of problems. And I just was wondering whether this translates to one particular divergence there. But I guess isolating it is not going to be feasible.
Yeah, okay. My feeling is that when you do this Euclidean version of string theory, and that's what you are doing here, right? Both in closed and open string sector, and then analytically continuing. Then this problem that we see with gravity, that is roughly like doing the integral along the steepest descent contours. Okay? Because the problem with gravity is that the conformal factor has the wrong sign kinetic term.
That's right.
Right? So the integral seems to blow up rather than go down. But if you follow this procedure that you will always go along the steepest descent contour,
right,
then that can be given a finite.
There you essentially rotate the contour so that this divergence. You go to imaginary axis, say, of phi.
Exactly. So here also we are doing more or less the same thing, right? Because for the tachyonic mode, for example, you go into on the imaginary axis.
That's right.
So philosophically, I think that we are this uses the Euclidean path integral, just like we'll do in gravity, and you use the steepest descent contour, which means whenever you encounter a negative mode, you rotate the contour. So I think that part of the procedure we are following here as well. That whenever you see a negative mode, you rotate the contour.
Right.
But here you have a little more control because of this tachyon potential, right? Because you understand the tachyon potential, you know exactly how you should rotate this, right? That we choose this kind of contour to get a sensible result.
I have a different question.
Okay. Yes.
Hi. So in the loops that in the diagrams that you've written, you only consider open strings, and in particular loops of open strings. That's you said because you consider open string field theory as if you had integrated out the closed strings.
Yes.
Is that because in principle any theory of open strings should contain already closed strings in their formulation, as at least in the internal space, and you can add the closed string vertices? Is that an assumption, or?
No, I think we are not really making that strong assumption here. Right? All we are saying is that if we take, say, let's go back in some example, that this vortex, for example, this vortex over here, this contains the y goes to 1 divergences. We are assuming that we have already analytically continued the y goes to 1 divergences, and whatever result we get, we include as part of this vortex. So it's just that we are not displaying the closed strings explicitly, because they are not, our goal is to understand the open string divergences. Closed strings are already understood. Okay? So the F finite that we define, okay, this includes the closed string divergences.
So, and I was thinking more about the diagrams that you showed in the later part, in the later
so
part,
here again the same
with loops.
Yes, okay, I'm coming to that. Yeah, I think right here. Yeah, the diagrams with loops like this, right?
Yeah.
So what happens is that, for example, as V goes to 1, okay, this one collapses. So that's a divergence. Okay, as V goes to 1, that's a closed string channel, in fact, right? Because you can say as V goes to 1, this becomes 0, right? Okay, so that's becomes in the like a thin cylinder. The annulus in that limit becomes like this. Right? So this is the closed string channel. And you may wonder, where are those divergences, right? You expect a divergence from the closed string channel. Okay, at least non-analytically from closed string channel. And again, the point is that in the BRY analysis, yeah, of course they have them. You wrote down integral 0 to 1 dv and various things. This part, what we call the divergent part, this didn't have any non-analyticity as v goes to 1, right? This was perfectly smooth as v goes to 1. So one may ask, where are the singularities as v goes to 1? They are in G finite. Okay, we also have the G finite of v and x, sorry, G finite, okay, which includes the v and x integrals. Okay. So all the closed string divergences are hidden here. It's just we are not calling them divergences because you can handle them using analytic continuation.
Yes. But this is still tree level in
closed string channel.
In closed string channel.
Yeah.
In the in the Feynman diagrams that you were drawing, there's also loops with open strings. If I put a closed string in one of those diagrams, is that just absent or lower, higher order in GS or?
Okay, let me go to the Feynman diagram again. So you want to put a extra closed string?
No, not extra, but is it possible to replace one of those open string loops by a closed string loop, or is that's just absent?
That will be higher order.
Okay.
This will be higher order. Right? So to this order, it doesn't contribute. But even in higher order, right, because the closed strings carry momentum, you can handle them using analytic continuation.
Okay.
But certainly to order G string, right, there's a closed string loop. Because you can also, another way of saying this is the closed string perturbation expansion goes in parts of GS square, right? So closed string loops will always go as GS square, whereas what you are calculating here is of order GS. So the closed string loops don't contribute to this order.
Nice. Okay.
But all I'm trying to emphasize is that even if they did, okay, or even when you go to higher order, they will start contributing, of course. You have to take into account those. But because the closed strings, the divergence associated closed strings can be handled by analytic continuation, you don't really need to use the string field theory machinery, at least a full form of string field theory machinery, to deal with those divergences. So you can again imagine that those have been all integrated out. Okay, they are dumped into the definition of the vortex or the finite part. And you can focus on the divergent part that comes from the open string degeneration. Here, for example, the v goes to 1 limit, right? You can ask which of these Feynman diagrams cover the v goes to 1 limit. And the v goes to 1 limit basically is contained in either this or this. Okay, you don't see these. So these diagrams, for example, don't have the v goes to 1 limit. Right? So this one has closed string loops and the apparent divergences associated closed string loops. But that's because it's a finite, we don't worry about this.
Okay, thank you. One final question: which one at the end of these slides that you got one half, which is the one that is there's a mismatch with VRY?
So that's the constant part of G, right? It's, you can see that when you add all of this, right, it's an omega independent part. So it's this part. Okay, it's this part completely, and then here it's this. It's the whole thing. Right? There's omega dependence here. Here it's this part and this whole thing, right? All of these are omega independent. So after you add all this, you get this minus half.
So it's hard to see that there should be a modification of one of these formulae without spoiling the nice cancellations. And
yeah, meaning, okay, you can say, okay, maybe this is wrong, right? If this was not there, this half is coming from there. But of course, that's a somewhat cheating, because I mean, you could have added and subtracted half inside lambda tilde, right? This is another parameter. And then it appears somewhere else. And what one finds that if we try, imagine that this half comes from certain set of terms, and you can ask what happens if we drop those terms. And what you find is if you try to drop those terms, then they also carry dependence on some other parameter. And that parameter dependence doesn't cancel. So it's very hard to make local changes in the calculation to get rid of this half. it may still be possible. As I said, I mean, I have tried for 6 months and failed, but it doesn't mean that it's not possible, right? Maybe there is some simple mistake, or there may be some conceptual issues, right? That besides these 4 effects that I have written, that
Or
the
is there is there a possibility that the matrix model calculation is somehow misses something, because that is also, is that possible?
It's possible, but it will be hard to imagine that missed something in such a way that all other coefficients agreed except this minus half.
Yeah.
Right? I mean, it's very hard to see how you can make, again, local changes in the matrix model calculation to make just change one coefficient.
But they come from some divergence. In matrix model part, it's coming from some regularization of the divergence.
No. From the matrix model is perfectly finite.
Finite.
Everything is finite. It's a finite answer that you're expanding in a sum of the perturbation term and the instanton term.
I see. Okay.
So there is no divergence on the matrix model side. Right? These apparent divergences are all on the string field theory side of the calculation.
I see. So you mentioned there is some numerical calculation that, of course, that cannot be wrong, but
okay, the numeric calculation basically is the following: that this G finite, the F finite and G finite, in order to match with the matrix model, right? You have to calculate these, because matrix model doesn't know about the splitting, right? It knows about the whole thing.
Oh, I see. Yeah. Yes.
So this G finite has to be calculated, right?
Yes.
And that was done numerically. Okay, so this is the BRY result. So if somehow that numerical analysis has some bug which puts a minus half, that would explain. But it seems unlikely that it's exactly a minus half that went into the numerical analysis.
I guess they have also tried to look for.
Yeah, exactly.
For a mistake, maybe, or
yeah.
And you mentioned the supersymmetric case also have the same problem.
Well, the supersymmetric case, the calculation is still being done. See, they are doing. Okay, I'm doing the analog of the normalization, and they are doing the analog of this F and G calculations. So there, the calculation, I think, is still not complete. Okay, because of this, I mean, the main complication is that you have this picture changing operators, and you have to be very careful to make sure that I put the picture changing operators in the correct place and so on. But the principle is straightforward. Is that that calculation has not been completed. So you don't know if for superstrings the results agree or not.
This must be way past lunchtime for you, Ashoke.
Yeah, it's just about lunchtime, I guess.
So unless there is a more pressing question, maybe it's about time we close. And of course, thank you very much for this last 3 days.
Thank you very much.
I really love the way you went through each and every step of this.
Thank you.
I'm going to come back to the movie and I come back to your papers to make sure.
Thank you very much.
Thank you very much.
Thank you.
And thanks a lot for everybody here.
Thank you.
All right.
Bye. See you.
Bye.